Recording is rolling. It is Monday, October 28th. So I have a Kahoot lined up for you guys. A bunch of guys jumped on the Kahoot. We'll do a few demos, got a couple Polyhute videos and what to round out today. My plan is this next couple days, let's do those textbook puzzles that you guys have had for a while that you could probably solve by now, but I'll help you guys a little bit out next couple days. I'll pick those up by the end of the week, but hopefully by the end of Wednesday they'll be finished anyway. And then I'll get you guys your next take-home quiz here pretty soon that is eventually going to be due this coming Monday. Right, so you guys will have some time to do that. Oh, Thursday, Friday, I have some other activities and at least another lab I'd like to do. So if I don't get to do everything I want to do, then there might be a review activity in the future. But right, there'll be plenty of stuff to do. All right, so back on Thursday and Friday, we were finally introducing this universal gravitation. So let's say between the Earth and the Moon, for example, there's some gravitational force. Okay, guys, which pulls more? The Earth pulling the Moon or the Moon pulling the Earth? Equal. That's Newton's third law, isn't it? Newton's third law. And the magnitude of that equal and opposite force is, well, GMM over R squared. So it's proportional to each mass. Just multiply the masses together. It's inversely proportional to the distance between them squared, right? So whatever this distance is, whatever the distance squared. You guys remember last week we were talking about an inverse square relationship. I was using a candle as an example. And if you want to make this an exact equation, you have to multiply by this universal gravity constant G, which is this number right here, which Vaughan and Jolly figured out back in 1880. You guys remember that? You remember that? All right. Now, there's different applications of this. Guys, one application is, could you use this to solve for your weight? Your weight? Guys, you sit in your chair. The Earth is pulling you down with the gravitational force. That's this force right here. Here, you plug in the mass of the Earth here for big M. Your mass could be little m. First, here's G right here, obviously. And guys, you sitting in your chair, what would you plug in for this R right here? What distance does that represent? If you want to solve for your weight. Guys, this is the radius of the Earth. Yeah, you just plug in the planet's radius because you on the surface. Here's another way to say that is what is the distance between you and the Earth? Well, from the point of view of this equation, it is the radius of the Earth. Right, so we're going to take the Earth's mass to be at the core, right? And you at the surface, well, it's one Earth radius away, right? So okay, so you guys got all that? Yeah. All right. What else we got? I think we also started to be talking about orbital speed. Actually, that's one of my demos. Maybe I'll go ahead and play this right here. Let me find Paul Hewitt. Where's here we go. All right, so you guys are about to be getting a Paul Hewitt.
Here's the world. And let's suppose we put a bowling alley up in the sky. We'll put it up in the sky to get away from the air drag. Oh, about 50 miles up, yeah? We'll kind of get it supported there so it doesn't fall down. Big structure. This is first-class bowling, man, okay? Now you take that bowling ball and you roll it. When it's here, the force of gravity acting like that. When it gets over here, force of gravity acting like that. Is that down? You're onto that. And some people think down's always this way. Come on, put yourself in a frame of reference to the world. Get a cosmic view, yeah? Okay. How about here? Which way's down, gang? Australians know. Huh? Like that, okay? And everywhere here, note how the force is pulling. Always perpendicular. And if it's pulling perpendicular, then there's no component along the alley. So once you've got it rolling, how's it going to roll? Steady, steady, steady. Unless you mess with it. Okay? So let's suppose I get it rolling at a certain speed, and let's suppose I cut part of the alley away here. Play a trick on it. Here it comes. I'm rolling at maybe like 4 kilometers per second. It's pretty fast. Here we go. Later on, come to the edge and hit, crash into the ground. Rolled it faster. Crash into the ground over there. Roll it faster. Boom, boom, still crash into the ground. I wonder there'd be a speed you could move it such that it would clear the gap. How many say, oh no, there's no way to clear that gap? Stand up. Come on. Is there see if you're sitting next to someone can calculate in their mind, or reason in their mind, or come up with the answer, how fast it gotta go to clear the gap?
Ooh, who knows the answer to that question? Maybe you're looking at your notes from back on Friday, possibly. Back on Friday notes, maybe. How fast does it take to orbit the Earth? It's the same question.
What'd be the answer, gang? Past tense of eat? 8. 8 kilometers per second. You're going to clear the gap. How about if you make the gap this big? Whoo, going to clear that gap? How about you make the alley this big? Here's the alley. Now here's your gap. Get it going 8 kilometers per second. What are you going to do? You're going to clear the gap. You come right back again. Take it away and send it on. Hey, huh? So it keeps moving at steady speed because it's always being pulled sideways to the way it's moving, yeah?
All right, so now we're back here. Yes, he's talking about orbital speed. So here could be orbital speed for a circular orbit. Okay. Yeah, I'm pretty sure this was in your notes from Friday, I want to say. Okay. Where, okay, you're on a curved path, there's some kind of centripetal force, and it's provided only by gravitational force. This is from the point of view of a satellite. Okay. So yeah, there's a gravitational force on the satellite. If we draw a free body diagram, this is the only force acting on, say, International Space Station could be, okay? Acting as a centripetal force, and you can solve for this V. Guys, what variable completely canceled to get to the orbital speed? Yeah, the little m. Yeah, the mass of the satellite. Yeah, so if you have a small satellite next to a large satellite, it doesn't matter. They need the same orbital speed, same orbit. Okay? If you run the numbers, so put in universal gravity constant here, the mass of the Earth here, let's call this approximately the radius of the Earth. Right, we're talking about low Earth orbit. It's probably not that different anyway. Take square root. I think the number we got was like 7,907, I think, meters per second, and you just rounded that up to 8 8 kilometers per second. Said right. That's what it would be, which give you a slightly elliptical orbit, which is ideally actually what you want anyway. All right, you guys ready for Kahoot? Kahoot. Oh, here we go. Oh, look at you guys. Look at you guys go. Kahoot time. All right, we're gonna see who's gonna win. Who's gonna win the Kahoot? Newton had the original insight to see what did Newton see that nobody before Newton understood. Newton was the first guy to understand that. Okay, what I'm looking for is the force on the moon is the same nature as the force on an apple. Earth pulls down on an apple, the apple falls down. Earth also pulls on the moon. The only reason the moon doesn't fall down is because it's moving so fast to the side, like a tangential type velocity. Right? Right. All these other statements are true statements, but people knew these for thousands of years before Newton. Like the moon is moving and orbiting the Earth. Like people knew that forever. Hey, what's this one? The moon always keeps one side toward Earth. You guys ever notice that? You guys ever notice there's only ever one side of the moon facing the Earth? You never see the opposite side. In fact, before 1957, we never sent anything to space. We had no idea what the other side even looked like. So that's true. It's called tidal locking. It's related to the tides. It's like tidal locking. There are a number of moons in the solar system that are tidally locked like that, right? I mean, but Newton wasn't the first person to figure that out. Newton was the first person to figure out this green one right here. That's what I'm looking for. All right, we got some points on the board. Henry, Wyatt, Samuel, Alexander, Cameron. Question number 2. Newton hypothesized that the moon what? Yeah, there you go. All those. Right, is falling around Earth is attracted to the Earth. It's a projectile that's just falling around the Earth. There you go. All those are true. Figured that one out. Yeah. So hey, if you take that apple and threw it to the side fast enough. I think Kahoot updated their program, so you can see guys sliding around here. But I've got Henry, Devin, Cameron, Wyatt, and Samuel taking first spot. Newton reasoned that the gravitational attraction between the Earth and the moon must be okay. Now, reduced by distance means this. Means that because the further the distance between two objects, what's happening to the gravity force? It's getting what? Smaller. Yeah, smaller and smaller. Yeah. Because it's specifically 1 over the distance squared, isn't it? Right, proportional to. All right. Now, guys, this red one and this yellow one say the same thing. The same at all distances, independent of distance. That means the same thing. But that means like if you double your distance, you get the same force. No, that's not true. Right. Right. Is it true the further the distance, the less the force? Right? So reduced by distance is what I'm looking for. That's that. 1 over the distance squared. We got Wyatt, Julian, Samuel, Gavin, Cameron. If the mass of Earth increased with no change in radius, what would your weight do? Yeah, would increase. Here, maybe I can back these up with the formula too, right? Because here's what we're talking about, right? If the mass of the Earth increased, but everything else stayed the same, suppose the mass of the Earth somehow doubled, but the radius stays the same, then your weight, like this force between you and the Earth, would also double. You see it? Right? And the question before that was looking at this type relationship. Say, well, if you spread these out further apart, right, the star would increase, therefore the force would decrease, and something like that. The previous question. All right, back over here. Boink, boink. Is that okay so far? Right, you guys got any question over it? All right. All right. Gavin, Brady, Henry, Samuel, Cameron. Fire. If the if the radius of the Earth decreased with no change in mass, what would your weight do? You're gonna squash down the Earth, right? Crunch it down. Now you're walking on the surface of a highly packed little ball Earth. What's happening to your weight? Ooh, all right, pretty good. This is a pretty tough question, but I'll show you guys why you would actually weigh more. You would actually weigh more. Why would that be? Right. Okay, so universal gravity constant, the mass of the Earth, your mass. Let's say that all stays the same. Like none of that numerator is changing. But if you pack the Earth down, you squash it down. You guys see that? That little densely packed Earth. Right. The radial size would be smaller. Hey, guys, you would be taking a fraction where you'd be 1 divided by a smaller denominator. Guys, if you divide by smaller numbers, what happens to the overall fraction? It gets what? Bigger. Yeah, you could try that out. You like actually got kind of an example right here. Right. I'll probably show this a few times throughout this Kahoot. This could be helpful, right? Let's go from like here to here. Or no, sorry, the other way, the other way. We're going from here to here. Right. So say you run GMM, it comes out to 100 units of something. Let's say the radius is like 2 units. I'm leaving the units off, but you just get the idea. Right? So 100 divided by 2 squared. That 100 divided by 4 is like 25 units. This could be newtons, pounds, whatever, some kind of force unit. 25 of those. Okay? Now, we're gonna squash down the Earth, maybe like half the radial size, which is this one down here. The GMM stays the same. And now it's divided by 1 squared. Hey, guys, if you specifically have half the radial size, all else equal, you have how many times the weight? 4. Get it? Because it's 1 divided by a half squared. It's like a factor of 4. Now look at that. Factor of 4. Lydia, Gavin, Brady, Samuel, Cameron. If the Earth's mass decreased to half of its original mass with no change in radius, your weight would what? Decrease to yeah half your weight. Here, let's take a look at the equation to back that up. Okay. So we're saying GMM over R squared. You run it, get some number. That's your weight. Okay. Then we take the mass of Earth and make it half of what it was before. Well, guys, if I throw a 1/2 factor here, this is going to come out. Your weight's also going to be half of what it was before, like half and half. It's a direct relationship there. Like that. Is that okay? What it would be half and half? All right. Emily, Devin, Brady, Samuel, Cameron. The gravitational force between two massive spheres. Yeah, there you go. All the above. Right. So is always an attraction. You guys notice that this gravitation is always an attraction? The next semester, when we talk about electricity magnetism, there's going to be some similar looking formulas, but you could also have a repulsive force. That's next semester with electricity. But for now, gravity, we'll just say gravity attracts. So always an attraction. Right? The more mass, the more gravity attraction. The more the distance, the less gravity force. Okay, that's an inverse square relationship. That's what I was saying. Yeah, all the above. Yeah, all the above. Those are all true statements. All right, Lydia, Emily, Cameron, Brady, Samuel. Which force is larger? The moon pulling on the Earth or the Earth pulling on the moon? Yeah, equal. And that, oh, guys, that's Newton's what law of motion? Third, Newton's third law. The first law was law of inertia. Second law was F equals ma. Third law, equal and opposite forces. Yeah, Earth and the moon, it's same force, opposite. Lydia, Brady, Emily, Cameron, Samuel. The gravitational force between two objects, let's call it 100 newtons. If the distance is cut in half, then what's the new force? Half the distance. First of all, is the force getting stronger or weaker? Stronger, they get closer together. Stronger force. Talking about 1 over the distance squared. Two winners. Two winners. Here, let me try to convince you guys that's going to be the case. So I could just point to this to say, guys, if I throw a 1/2 factor on that r, here, write this down. Throw a 1/2 factor on that r. Let's say f original, it's like gmm over r squared. Okay. Well, let's do this in terms of variables. How about that? That'll be fun. I haven't really done this all day today. G, let's call this force new. Call this like force original. Okay. Gmm over, and I'll have half of the original radius and square that like that, right? So good? So far, all good? Okay. Right, so F new equals, all right, well, 1/2 squared. So got gmm up here. This is like a quarter down here of r squared. Like I said, guys, what is 1 divided by a quarter? What is that? Does anybody know? Guys, what is this? What is 1 divided by a quarter? What is that? 4. Yeah, put a little thought cloud right here. Yeah, 1 divided by a quarter, that's 4. So that's what this is right here. This is 4 times gmm on r squared. Right. And gmm on r squared, that was the original force. Right there. Right. So the new force is 4 times the old force. All right. There you go. There it is in terms of variables. Okay. Yeah, you could make up any numbers. You could call, let's call it G1, M1, M1, R1, you know, whatever numbers. Just, you know, lots of numbers, hard numbers to look at. Okay. But it's always that proportion. Yeah, it's like that. Okay, so 4 times the force. Okay, and if the original force was 100 newtons, 4 times that is just 400 newtons. It scales up by a factor of 4. 1 over the distance squared. Okay. Are you guys getting it with 1 over the distance squared? We got Lydia, Brady, Emily, Cameron, Samuel. Ooh, it's a tight race too. The force of gravity on you is greatest when you are standing where? All right. Yeah, pretty good if you got that right, because we hadn't actually covered this yet. So here, I'm gonna walk you guys through a story. Let's take a couple minutes. That'll be right. Okay. So here I got a graph of Earth's gravity field as a function of distance from the center. So it starts at 0, could be the core, right? Right, and then you go out from there. Right. Here, capital R could be the fixed radius of the Earth, right? And then you could go beyond that and you take off in a ship. You guys see that, right? Okay. If you want to, instead of on the vertical axis having gravity field, could you just call that your weight, like a force, right? which would be the same basic shape graph, right? Same shape, same story, right? Now, all of us have lived our entire lives at the surface. We all experience this gravity field, and we all have some weight. That's this point right here. That's all our brains really understand, right? Like from a first-hand point of view. It's just this point right here. That's all we know. We're at the surface. We're in this gravity field. Got whatever weight. Okay. Now, you guys ready for this? Suppose you. Oh, you guys see this big old tower here? This 1 Earth radius tall. Right. No. Does that look like the Leaning Tower of Pisa? I think I probably just copy pasted that from some animation I had because that animation graphic probably took me a while to make on my computer screen. Okay. Guys, is the Leaning Tower really 1 Earth radius tall? No. All right, that question came up earlier, right? But it's not really this tall. I'm just doing a just for the animation. But if you effectively double your distance from the center, guys, if this guy on the surface weighs 100 pounds, I weigh 100 pounds. And he climbs this tower and brings the bathroom scale with him and steps on that scale. How much does he weigh at the top of that tower? 25 pounds. Because he's double the distance away. Guys, double the distance away. Throw a factor 2 on this R, gets squared. That's 1/4 of his weight. Right? 1/4 of the force. Okay. That's, by the way, on this graph, that's this point right here. You see where you double your distance right here? You get, look at that. It's 1/4 of the gravity field, 1/4 of the force. Right? Right. And then you take off in a rocket and you fly away. Guys, everybody focus here. As you get further and further away from Earth, what's happening to the gravity field from Earth? Getting less and less. Suppose this rocket gets all the way out by Mars. Because when you're out by Mars, is Earth pulling on you? Okay, you could say no. And maybe that's approximately true. If it pulls on you all, it'd be a tiny, 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 tiny bit, maybe, right? Right? Because it's 1 over the distance squared. So, yeah, even no should be an acceptable answer. Because, guys, this curve asymptotically approaches 0. You see it? Asymptotically approaches 0. Okay. Now, let's tunnel down into the Earth. You guys ready to do journey to the center of the Earth? Look at this guy. He's got a little shovel. He's gonna dig a spiral staircase all the way down to the center. Now, let's make believe. You guys know the center's all molten and hot and crazy stuff, right? Okay, we're gonna ignore that. We're gonna just assume, just make believe that's all just like dirt all the way through, right? Okay. And he gets to the center and like tunnels out a little cave down there. He brought his bathroom scale with him. Guys, how much does this guy weigh right at the center? 0. Okay, you guys get that? Because I ask that question every year, and there's like half the students think 0, and half the students think, wait, wouldn't he weigh a lot or something? All right, it's 0. Right. Here's why 0. Well, that scale that he brought with him, he has no floor to stand on. I mean, maybe that's one hint. There's no ground to stand on even, right? He'd be floating around like an astronaut. Right? Also, guys, how do you even have weight? Because the Earth is pulling you straight down, right? But wait a minute, isn't the Earth kind of made of like quadrillions of little grains of sand, right? And every little grain of sand pulls you its own direction. But the net effect, if you're standing on the surface, the net effect is straight down. Yeah, a lot of them pull you straight down, sure. But this pulls you a little bit to the left. This one pulls you a little bit to the right. The left-right cancels, and the net effect is straight down. So you're pulled straight down, right? But when you get to the center, doesn't every grain of sand pull you a different direction? And it all cancels out. Okay. So you weigh 0 right at the center. You guys get that? 0 right in the center? Okay. All right. One more piece of this. One more piece of the story. Let's suppose you're halfway down the spiral staircase. Remember, he brought his bathroom scale with him, right? Right. He stands on the scale right there, just halfway down to the center, right where I'm pointing, right? Now, if he weighs 100 pounds on the surface, how much do you think he weighs halfway down to the center? Yeah, half of his surface weight, like 50 pounds, right? Now, I didn't actually prove that to you guys, but you can prove that, right? You have to, maybe we'll possibly save that for a different day, right? But just go ahead and take my word for it now. This is true as long as there's uniform density all the way through. That would be this line right here. So I'm making the claim without proving it today that this is a linear relationship as long as you're inside the planet. Okay, you guys get that? All right. So let's go back to Kahoot. All right. Yes. Okay. So the most you would weigh would be on the surface. If you take off in a rocket, get further away, your weight goes down. If you tunnel down, deep tunnel into towards the core, your weight also decreases. Okay. You weigh the most at the surface. Got Emily, Henry, Cameron, Samuel, Lydia. Ooh, lead in. You will lead. The reason the moon does not fall into Earth is why? the moon has sufficiently large orbital speed. Tangential velocity, could have said that too, right? Not that okay, we knock out the gold one first. Gravitational pull of other planets keep the moon up. Okay, that's just kind of a silly answer. Okay. Also, not necessarily because of different masses either. Let me tell you guys a little bit about that. Let's go back over here. So, show you guys a picture. All right. So here could be, I'll call it E for the Earth, right? Center mass. Call this M for the moon. I think that may be pretty close to scale. So something like that, right? Like that. Right. Now, these two, gravitational attraction, the moon is orbiting the Earth, right? Moon is orbiting the Earth, right? I'll usually say that. Here, I'm gonna go detail more technical. Technically, both the Earth and the moon are orbiting a point called the barycenter, which is I think it might be the center of mass between the two. And if it's not the center of mass, maybe it's something pretty close to that, which is right about here. You guys see where I put the little X right there? That could be the barycenter, which is inside the Earth, but it's not the center of the Earth. Okay. Okay. Oh, do you guys think it's possible for a planet to have a moon so large that the barycenter is actually outside the surface of the planet? Right. Pluto, as I know Pluto is considered a dwarf planet or whatever. You guys get the idea. If this was Pluto, one of its moons is called Charon. I don't know if this is exactly to scale, but you guys get the idea. Pluto and Charon, and they actually orbit a point that's probably right about here. So they're like both orbiting their barycenter right about there, right? Yeah. So if you blew up the mass of the moon bigger, 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 the barycenter would move, but you could still have the orbital mechanics. They're just a little different. All right. So it's a little more details. Boom. Yeah, but I'm looking for sufficiently large orbital speed. Now it can orbit. All right, here we go. Henry, Brady, Lydia, Cameron, Samuel. You're the top spot. A lunar month is 28 days. Moon, month, same root word. If the moon were closer to Earth, one lunar month would be what if it was closer? Uh, yeah, less than 28 days. Okay, most of you guys got that. Awesome. All right, let me make a connection here. So going back to where's my orbital poster? This orbital speed. Right. Oh, all right. So the further out the moon is, I mean, if it, guys, let's start at low Earth orbit. Low Earth orbit. You're orbiting the Earth pretty close to the surface of the Earth, pretty much one Earth radius out. Right. That could be the International Space Station. Is that going about 8,000 meters per second? No. What's the past tense of E? Dang, 8 kilometers per second. Okay, that's low Earth orbit, right? And then as you go out, isn't it true you're going slower, slower, slower? Also, guys, what happens to the circumference of the circle that it takes? Well, not a true circle, but pretty close to a circle that it takes to go around. Isn't that getting bigger the further out you go? Proportional to r, circumference equals 2 pi r about, right? So for both of those reasons, it has to go further, and it's also going slower. It takes more time to go around. So it takes the moon 28 days to go around. You guys got that? 28 days. How long does it take a low Earth orbit satellite to go around the Earth? How long? Yeah, about 1 hour and a half, about 1.5 hours, about 90 minutes. So if you're on board the International Space Station, you see a new sunrise every about 90 minutes, right? And what this kind of reminds me of is kind of this right here, right? So the further out you are, R, the more time it takes to go around T. And the Kepler relationship right there. You guys remember that? All right. Anyway, so as you back up from low Earth orbit to the moon, it takes more and more time to go around. One special point is called a geosynchronous orbit, right? So do you guys think there's some satellites out there that take 24 hours to go around the Earth if they're far enough away, right? And then from the point of view of Earth, you look up in the sky and it looks like it's just kind of hovering there. It's called geosynchronous. So I think that'll come up one of these days pretty soon. Got Wyatt, Brady, Samuel, Lydia, Cameron. Ooh. A planet has half of Earth's radius, but the same mass. Suppose you were on that planet. How much would you weigh? Hmm. I think you guys saw this question earlier today. Did you guys see this question already? Right? It said like, here, if you like pack the Earth down into a little tiny ball where it had half the radius, but it was the same mass, right? That's kind of like this right here. So let's say the original R was like 2 and did 100 divided by 2 squared, got like 25 force units, 25 pounds, right? And then you pack that radial size down to half of what was before. Half of 2 is 1. 100 divided by 1 is 100. You guys see the force would go up by a factor of 4, right? 25 times 4. You guys see that? So let's see how you guys did over here. You guys got, hey, 4 times your weight, right? You guys get that? Right? So it's an inverse square relationship. 1 over the distance squared. 1 divided by a half squared. That's like 4 times. Okay, is that okay? All right. I got Brady, Samuel, Lydia, Wyatt, Cameron. The mass of Jupiter is 300 times that of Earth, but you only weigh 3 times as much. Why? Yeah, large radius. There you go. All right, see you guys good? Large radius. Looking good. All right, Brady, Samuel, Lydia, Wyatt, Cameron. 4 points. You stand atop a ladder that's 1 Earth radius tall. What would you weigh at the top of the ladder? Here. You guys remember this guy? Guys, if you're on top of a ladder that's 1 Earth radius tall, then what's happened to your distance from the Earth climbing that ladder? You're not how many times as far away? Twice as far. Twice as far. And if you double your distance r, what happens to the gravity force between you and the Earth? Quarter. Yeah, because 1 over 2 squared, 1/4. And remember, that's exactly this point on this graph right here, right? Twice as far out, get only a quarter of this original force. Right? Okay. Well, this shows a quarter of the field, but it's proportional to that. Same thing. All right, let's see how you guys did on Kahoot. You got that. All right, about half the class got that. All right, 1/4 of your surface weight. There you guys go with 1/4. 1 over the distance squared. We got Lydia, Samuel, Brady, Wyatt, Cameron. Since Earth is attracted to the sun, why doesn't it fall into the sun? That would make your day. That would be that would make my day, Brian. Yeah, I'm looking for guys sufficient tangential velocity. That's it. All right. So suppose let's just focus on the Earth and the sun. And let's say there's nothing else, just the Earth and the sun. So the Earth is orbiting the sun, right? I guess they're orbiting the very center. Let's say the Earth is orbiting the sun. From the point of view of Earth, if you drew a free body diagram on the Earth, would it have a gravitational force pulling it towards the sun? Yeah. Would there be any other force? Nope. That's it. That's the only force. That only one force, the gravitational force, is acting as a centripetal force, right? But that there would only be one force. That's it. Right? There, guys, is there an equal and opposite force to the sun pulling the Earth? Yeah, the Earth pulling the sun, but that doesn't act on the Earth. That acts on the sun. That's why it's not the green one. Okay. So the yellow one is what I'm looking for. Okay. All right. Got Devin, Wyatt, Brady, Samuel, Cameron. 440 Newton man stands on top of a ladder 1 Earth radius tall. What's his weight up there? We talked about this a few months ago. 1 Earth radius tall, you've doubled your distance from the center. 1 over a double squared, it's like 1/4. Aha, 1/4. Aha. Let's get that. All right. Gravitational force between two masses is, let's say, 40 newtons. If each mass loses half its value, half the mass, what's the new force? Uh, yeah. So a half times a half is a quarter also. A quarter of 40. Let me find. Here, get back this up with this equation then. So if this mass is reduced to half and this is reduced to half, I got a half times a half. That's a quarter of the overall force. A quarter of 40 would be 10. Let's do that. What do here? All right. The gravitational force between two spheres is 20 newtons. If the distance is cut in half, what's the new force? You guys know a little bit. You guys, if they get closer together, is the force getting bigger or smaller? Right? Half the distance. What's 1 divided by a half squared? Ooh. Okay, so here, go back over to this it's right here. Okay. Guys, you're thinking. Guys, if you cut the distance in half, I'm throwing a 1/2 factor on this R. Guys, what is 1/2 squared? Is that like a quarter? Right, 1/2 times 1/2 is 1/4. What is 1 divided by a quarter? It's 4 times. Right? So 4 times. So back over here. I do it. I have a better version. All right, that's kind of like this, maybe. Okay, actually, this could exactly be it, right? Because I cut the distance in half from 2 to 1 meters, whatever, right? I'm getting 4 times the force as a result. All right, so there you go. Step before. All right. Gravitational force between two spheres is 40 newtons. If each mass loses half its mass, what's the new force? A half times a half. Half times a half is a quarter. A quarter of 40 is 10 newtons. Okay, let's go there. Here, let me draw something for you guys. I've been saying that 1/2 times 1/2 is 1/4 infinite, right? Because it's like half of this gives you a quarter overall. Right. My earlier classes have been drawing pizzas. Say, what if you buy a pizza? You chop that in half. Now you got 2 halves. You take one of those halves, chop it in half again. That's half of a half. Isn't that right there? Like a quarter of that pizza? Yes. Sam, I didn't know a little visual right there. All right, we got Wyatt, Samuel, Devin, Brady, Cameron. 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. What's that look like? There you go. Move the decimal place 11 places to the left. All right, and for the win, 5.98 times 10 to the 24 kilograms. Guys, that right there is the mass of the what? That's the mass of the Earth. Yeah, mass of the Earth. That's what you're sitting on right now. Yeah, there you go. Mass of the Earth. Let's see. Winners with with bronze, Samuel. With the silver, Brady Z. With the gold, Cameron. All right, nice job. I got just a few more things here, guys. A few more things. So I want to show you guys Lagrange points. I have a demo for this too. I'll walk you guys through the story. Do you guys think there's a point between the Earth and the Sun that the Sun pulls to the left as much as the Earth pulls to the right, and it's a wash? Let's call that L1. Now that point must be closer to the what? Closer to the Earth. Yeah, closer to the Earth. Right? Sun's more massive. Earth could be closer. It could be a wash. Okay. Now, when you consider orbital mechanics, do you think there could be an L2 point that everything's pulling to the left? You can kind of go along for the ride, and the Earth's always beneath your feet, but you never actually fall towards it? Yeah, L2. Have you guys heard of a telescope called the James Webb Telescope? That right now is orbiting this L2 point. Ooh, that's kind of cool. Right? Hey, if there's an L2, do you think there must be an L3? Kind of makes sense too. Right, kind of over here. Right. So a fancy math away. You guys see an equilateral triangle, another equilateral triangle, this L4 and this L5. All right. So let's do an animation here. Animation time. So here, zoom in. Right. Here's you guys see the inner plane. So the Sun, Mercury, Venus, Earth, Mars. Guys, what's this going around out here? Jupiter. Now, the biggest mass in our solar system is the Sun. It's like 99 point something% of the mass of our solar system is the Sun. What's the largest mass after the Sun? Jupiter. So between Jupiter and the Sun, it's going to drive a lot of the mechanics of our solar system. Guys, what's all these pink dots? What's those? Asteroids. Guys, that's the asteroid belt. That's the asteroid belt. It's all those little pink dots, right? Hey, does that look kind of triangular-ish? I think these are the L4, L5 points, Jupiter and the Sun. I think this is the L3 over here. And what do you think you guys see those green patches? This is called the Trojan and the Greek asteroids. They're more asteroids, just kind of stuck in the L4 and L5 points. All right, last thing today. Show you guys how Neptune was discovered.
Some people thought that gravity was rather local, and some evidence for that was back in the early 1700s when they looking at the planets. The astronomer types know that when a planet goes by Jupiter, for example, the planet coming around the sun like this, when it goes by Jupiter, it sort of wobbles a little bit. And that was to be expected because there's an interaction between the planet and Jupiter too, like the planet Uranus, okay? But when Uranus is way out here and Jupiter's over here, they found out that Uranus was acting a little differently out there too. They call that a perturbation. And they found out that the planet Uranus was undergoing a perturbation where no other planet was. And the popular idea at the time was, well, way out there, the law of gravity, Newton's majestic law of gravity, is obviously breaking down. But not everyone believed that. A couple of mathematician types made some calculations as to where another planet would have to be to cause those perturbations. And they made about the same time in history. One was an Englishman, the other one was a Frenchman. And the Englishman reported his hypothesis and sent it to the observatory in Greenwich, England. When the observatory type got his letter, opened it up and says, "What's this? Some mathematician is telling me that there's a new planet, so-and-so coordinates in the sky. What is this stuff?" I'm exaggerating. The Frenchman sent his findings to the observatory in Berlin. And the Berlin types said, "What's this? A new planet? If I turn my telescope so many degrees that way and so many degrees, I will find a new planet." Son of a bitch. There it was. They discovered a planet predicted by the law of gravity. And that planet they called Neptune. That's right. Neptune was predicted. That's the nice thing about science. If you know some science, it will allow you to predict things, see? And they predicted where Neptune was. Ain't that neat? And later on in 1930, this century, they found other perturbations of Uranus. And those other perturbations led to the discovery of what planet, gang? You know? Pluto. That's right, Pluto.
Yeah, so there you go. Planets discovered by mathematics.